Welcome to the lecture on Chapter 12, Linear Optimization Models. We'll be covering optimization models for the next three chapters. Chapter 13 we'll be looking at integer optimization models, and Chapter 14 will be dealing with nonlinear optimization models. As I mentioned, I'll be posting these on YouTube. And as a courtesy to YouTube, I'm going to try and keep all of the individual videos I upload less than an hour, so I don't upload these massive files, and I don't want to cause any potential overload problems with larger videos. So I'm just going to keep each one of these under an hour. So this lecture probably will be divided into two parts, maybe three. We'll see how it goes. So linear optimization models and optimization problems in general are part of what we do supporting customers. And we'll get into this lecture, but first let's review Monte Carlo simulation, the graded exercise from Chapter 11. And here we have the model for Chapter 11. Now, you will have turned this in before the class today, and let's go over this model. So Brinkley is interested in an analysis of the profit per unit they could make. Now, we set up a static model, and we had the selling price, total procurement cost, labor cost, and transportation cost as variables that affect the profit per unit. And if we look at the profit per unit, it's going to be equal to the selling price minus the procurement, labor, and transportation costs, as we see here in the formula bar. Once we had the static model defined and the customer agreed with us on this is what we want to go forward with, then we introduced randomness. In other words, the procurement cost, labor cost, and transportation cost are random variables, meaning that they don't have one value that we can expect in the future, but instead they'll have several different values that we might expect and a probability associated with each one of those values. In the case of the Brinkley problem, the three random variables, the costs, have a discrete probability distribution associated with them. In other words, they have a very few number of values that they can take on, and we have an estimated probability for each one of those. And the way we set up our table for that probability distribution is we're going to use a random number generator to generate a number between 0 and 1, and we just reflect the percentage of times that it might occur between 0 and 1 and associate that with the probability that was estimated for a particular cost. So for the cost of $10 with a probability of 25%, we go from 0 to 0.25 in our upper and lower ends. And then likewise for $11, 45%, we start at 0.25 and go to 0.7. And likewise for the other values in our distribution. That way, when we generate the random number, 25% of the time we'll get 10, 45% 11, and 30% 12. Likewise with the other tables, the labor cost discrete probability distribution is in this table, and the transportation probability distribution is in this table. So we look at the actual function we put in for our random variable, in this case procurement costs. We're doing a VLOOKUP, and the value we're looking up is going to be generated by a random number function. That will then be searched in our table. When it finds an approximate match, because we set approximate match equals to true, it will return the value in column 3. And of course our table is 3 columns A, B, and C. So it'll return the cost. Likewise for the labor and transportation random variables. So we've defined our random variables and we've defined the function of interest. Let's go ahead and create a Monte Carlo simulation for those. So I'm going to go ahead and put the function for procurement cost, which we've already defined in B5, here. So I'll say equals B5. Likewise, let me get the mouse out of the way. Likewise, labor cost, so I'll say equals B6 here. Transportation cost equals B7. And finally, profit per unit, which is going to be B28. And now we've got our random variables defined and our simulation trial. I have a simulation trial going for 1,000, so I'm going to highlight our random variables, and I'm going to do Control-Shift down arrow, and that'll select our list for 1,000 trials in our Monte Carlo simulation. Next, I will go up to the Data tab, and on the Data ribbon, I will go to What If Analysis, Data Table. And I'll put D1, some empty cell in there. And it calculates for us 1,000 different trials with the random number generator for each one of those variables. So we get a variety of interactions of the randomness of procurement, labor, and transportation costs. And we now have a column, profit per unit, that is a list of 1,000 different profit amounts based on our model. Once we have that column, then we can go over and get our profit per unit statistics. Of course, our count's going to be 1,000, and we can use the count function E31 to E1030. We can get the minimum, again, the min function on that same column of a profit per unit. Maximum, the max function on that same column of profit per unit. The average, or in other words, the expected profit per unit that the company will look at. Standard deviation, again, all these are standard functions in Excel. Now, to get the probability that the profit would be less than $5 per unit, what we'll do is, let's look at this, use the COUNTIF function. So on our column of 1,000 trials and the profit per unit for those 1,000 trials, we'll look at counting them if the profit is less than $5. Then divide that count by H31, which is 1,000, and that'll give us the probability that their profit they're going to make is less than $5. So the probability that they make a profit of less than $5 is 7%, about 7.3%. So now management has better insight into this particular product than they did before we did our analysis. We can further help them by doing a frequency histogram. So we'll set up some bins from 3 to 12 for profit per unit. And then we'll use the frequency function to do a frequency count in our profit per unit column from our simulation and count up how many we get, the count we get for each different dollar value. And of course, $6 and $7 are very high. The extremes, $3 at the low and $12 at the high, both of those are fairly low counts. And we can graph this and include it in our report that we send to them. So that's what we needed to do for the graded exercise in Chapter 11, Monte Carlo simulations. I'll close this one. So this chapter begins the discussion of prescriptive analytics and how optimization models can be used to support and improve managerial decision making. So, optimization problems obviously are going to improve management decision making. They'll be using data to make data-driven decisions. With optimization, we're looking at two things: maximize or minimize. So we're going to maximize some objective function, or we're going to minimize that. And both these terms go under the general heading of optimization. And they can be linear or nonlinear. The type of applications that we might see them in manufacturing, you're going to minimize total production and inventory costs. Financial analysts might use them to maximize the return on a portfolio. Marketing manager might allocate a fixed advertising budget to maximize the reach out to customers, potential customers. And a very popular one is warehouses. You have a set of warehouses and you have a set of plants, and you've got to get materials from the warehouses to the plants, and you want to minimize your total transportation cost. So those are the type of problems that we'll be doing this with. So linear programming was initially referred to as programming in a linear structure, and then in the late 40s, Challing-Koopmans suggested to George Dantzig that that name was too long and shortened it to linear programming. George Dantzig is a graduate from my alma mater, University of Maryland. He got his doctorate there in the late 1930s. And of course, he is the person who developed the simplex algorithm that we use in linear programming, which means that your objective function and your constraints are both linear. Okay, well, let's take a look at an example to help us understand the concept. So, Par is a company, as you might imagine, that makes golf equipment, and they're considering producing a new bag in two variations, a standard and a deluxe, so a golf bag. And they want to know what is the optimum quantity for standard and deluxe bags to maximize their total profit. Now, of course, businesses do not have unrestricted ability to change the quantities they make of anything. They're subject to constraints: budget, time constraints, hours available constraints. So we see the various tasks for making a golf bag: cutting and dyeing, sewing, finishing, and inspection and packaging, and the hours it takes to produce each one of the bags, standard and deluxe. So they're in that table here, the hours that it takes to do each one. And then we see the total available hours. In other words, we have workers that are able to do cutting and dyeing, and they can provide 630 hours of work per time period. The profit per bag we make is $10 and $9 respectively. So what we want to do is find out the quantity of standard and the quantity of deluxe bags that will maximize our total profit. Let's take a look at our total profit. This is a sum product. We multiply B9 to C9, in other words, our profit per bag for standard and deluxe, and we multiply those by B14, C14, which are the quantities for the standard and the deluxe bags. So I've just put 1 in as a placeholder for each one of those bags, and we see that our profit is 1 times 10 plus 1 times 9, or 19. Now, this is going to be subject to constraints. So we have constraints on cutting and dyeing of 630 hours. The hours used are going to be the quantities of B14 and C14, in other words, quantities for each type of bag, times the hours we spend, which is B5 and C5 for cutting and dyeing. Likewise for these. So obviously with one bag that we're producing for each type, we're well within our constraints, and this is a feasible solution. But it may not be an optimal solution. So we'll take a look at that. So again, PAR is this a small manufacturer of golf equipment and supplies. By the way, just for purposes of this problem, obviously, PAR's distributors agreed to buy all the bags they can make. Very popular company, apparently. And we've taken a look at that. So we're going to produce a model. So we're going to formulate our problem, and that problem formulation process is also known as modeling. It's where we translate a verbal description of a problem into a mathematical statement. And in machine learning, we would say we're translating a domain problem into a statistical problem or a mathematical problem. And the general process we're going to go through is we work with our customer to understand the problem thoroughly. We describe our objective function like we did in that spreadsheet. We describe each constraint, which we did, hours available for the various tasks, and the decision variables. Oftentimes the decision variables are going to be quantities. You're going to vary a quantity to see how you're going to optimize something, maximize or minimize. Then we write our objective function in terms of the decision variables, and likewise the constraints in terms of the decision variables as well. So here we've got our decision variables, which is going to be the number of bags produced, standard and deluxe. So S is equal to the quantity of standard, D is equal to the quantity of deluxe. Next, we write the objective function in terms of decision variables. So that's going to be total profit equals 10 times S plus 9 times D, because we make $10 profit on a standard and 9 on a deluxe. That's our objective function. Our objective is to maximize 10S plus 9D. Likewise, we'll write our constraints in terms of a function as well. Sewing hours available equals the coefficient, the number of hours for standard times the quantity of standard, plus the coefficient or the number of hours for deluxe times the quantity of deluxe. And this is a linear function, and that means that all of the constraint functions are linear and the objective function is linear. And with a linear function, we can use the simplex algorithm. So let's take a look at how we might solve this conceptually, and then we'll look at how we solve it with Excel. So we have this idea of a feasible solution. In other words, this is something where we get a value from our objective function, and the decision variables that create that value also satisfy all the constraints. In other words, none of the constraints are violated. So there's obviously a wide variety of possible combinations for that, and that whole set of combinations is known as a feasible region. Each one of those points is a feasible solution, and that's a setting of the decision variables that satisfies all of the constraints of a problem, and we get an associated value from our objective function. So here's a geometry of this particular problem, and 50 years ago when I was in college, this is how we would solve them. We would map a equation for each one of the constraints on a Cartesian plane just to give us an insight for what's going on. So obviously each one of our constraint functions defined in terms of the decision variables, number of deluxe, number of standard bags, forms a line in our Cartesian space, and they are all going to intersect, and this blue region is the set of points that satisfy or is less than all of the existing constraints. So a line for each one of the constraints is going to divide the total space into what is known as half spaces. And the intersection of the half spaces for each one of the constraints makes up this feasible region. A feasible region, again, is this set of points that satisfies all the constraints of a problem. And when the number of decision variables is 2 and the function is linear, they form lines in 2 space, which we see here. And if the constraints are inequalities, in other words, the total number of hours used for sewing has to be less than or equal to the hours available. Number of hours our workers with that skill can provide during that time period. These forms half spaces, and then we get an intersection with those half spaces. Next, once we have our feasible region, then we want to look at our objective function, which of course also is a line, and we can give it various values. So let's say let's test 1800 to see if that is an optimal solution, 36, 54. So of course these points are all in the feasible region, but we can still keep going up. We can keep going up with our contour for the objective function until it's tangent to our feasible region. And that's where we're going to get our maximum profit line. So in this case, our maximum profit line is 7,668. And it intersects where we have an intersection of our functions, our constraint functions. Now, in the old days, we used to get these intersection points, 1, 2, 3, 4, and 5, by just solving the equation. So you'd take one constraint equation, equal it to the other, multiply, add, divide, subtract, and so on, and you would get points where they intersected. And that's what we see in these extreme points on our feasible region here. Obviously, today we have tools like Excel. Python has libraries like pandas that help us do this. R has libraries that help us do this. SPSS and so on, SAS. So we have a variety of tools to help us do that. So we don't have to go through that tedious and laborious effort these days. But just conceptually, so you understand, this is what is being done behind the scenes for us now. So once we get the highest contour value is going to be where it intersects, our contour line for profit intersects with one point, a single point on our feasible region, and in this case it's 0.3. The other points where we have intersections between the constraint functions are extreme points of the feasible region. Let's go forward. Okay. Extreme points are found where constraints intersect on the boundaries of the feasible region. And we have, of course, several of them there. The approach of investigating only extreme points works well, and it generalizes to larger problems. And the simplex algorithm, and that was again developed by George Danzig, who got his doctorate at University of Maryland in the late 30s. A quite effective way at investigating extreme points in an intelligent way to find an optimal solution. Excel Solver is the tool we'll use, and that utilizes Danzig's simplex algorithm for linear equations. Obviously, if we have nonlinear, then we'll use a different algorithm for that. So let's go ahead and see how this works in Excel. And the first step that we're going to go through in Excel is to construct the relevant what-if model. And of course we've done that, and I've gone over that. And then you'll look at whether a trial solution is feasible and the value of the objective function at that trial solution. That's what we want to get. So, but what we need to do, and we've done that, and we've put in 1 and 1 for our decision variables for standard and deluxe golf bags. And then we got our profit, $19, and then it's feasible. So we did a trial solution. Everything seemed to work fine. Next step, we have to then convey to Excel Solver the structure of that linear optimization model. So let's take a look at this. Get this in here. So here's our model, and of course we've gone over this. Solver is on our data ribbon, so click data, and then over on the far right you have Solver. And it brings up a dialog box, and I'll just move that here. Our objective function, we put in the first text box, and of course that's going to be our total profit. And we went over that that is a function of the profit per bag times the quantity for each type of bag. What we want to do in this optimization problem is maximize it. And we're going to do that by changing our decision variables. In other words, the quantities for each bag. And those are in B14 and C14. Then we need to add in our constraints. So you do that by clicking the Add button, and then you can put in your cell and select a relational operator. Next chapter, chapter 13, we'll be doing integer optimization, and we'll be using int. But that's not today, that's in the future. Okay, so we enter our constraints in like that. Here, our constraint is going to be that B19 through B22, in other words, the hours used for the 4 functions, is less than or equal to C19 through C22, in other words, the hours available for each one of those functions. And we can select simplex algorithm, which we do, and then we're going to click solve, and it is able to find a solution. Now, before I click OK, I'm going to select answer from my reports. A couple of different type of reports. Let's look at answer first. So I'm going to click OK, and we see that we maximize our profit at $7,668, and we produce 540 standard bags and 252 deluxe bags. Our constraints are all satisfied. We didn't violate any. We notice in some cases, like with sewing, we actually have some slack time. In other words, we still have hours available. We have 120 for sewing, and then we have slack time for inspection also, about 18 hours, not quite as much. Well, let's take a look at the answer report that I wanted us to have. So, the answer report contains 3 sections. The objective cell indicates the optimum value of the total profit, and of course in this case it's 76.68. And the variable cells indicate the optimal values of our decision variables, and whether or not they're required to be integer. And of course in this chapter they're not, but next one they may be. So of course the decision variables are the quantities. And then the constraints section shows the left-hand side value for each constraint, hours used, the formula showing the constraint relationship, in other words, it must be less than the hours available, and if it's binding or not binding, and the slack value. And we went over the slack value and saw 120 and 18 for that. A binding constraint is one that holds as an equality at the optimal solution. They intersect to form the optimal point. A slack value again indicates the difference between the left and right hand values for a constraint, and we showed that we had a slack value of 120. Okay, let's minimize this. Okay, I'm going to stop part 1 of lecture 12 here, and I'll create a new video with part 2 of chapter 12, sorry. So hold on, and I'll create the second part